So we have to be aware of the challenges of the 21st century. As you know, geotechnology is a supporting discipline for all civil engineering disciplines. And whatever you do, geotechnical engineering is the starting point. So whether it is structural engineering, earthquake engineering, wastewater treatment, transportation, urban infrastructure, heavy industry, water management, dams, hill area development, construction management, everything requires the inputs of a geotechnical engineer. The thrust has to be to develop realistic design parameters, maybe encroach upon the factor of safety, but enhance the factor of reliability. So safety versus reliability, that's very important. So today, geotechnical engineering is evolving faster than ever, driving safer, sustainable, and smarter solutions for modern development. So the key role in the industry for the geotechnical engineer is to evaluate the subsurface conditions for safe and stable foundations, giving design solutions for challenging terrains, from urban skyscrapers to renewable energy sites to hill areas, deliver cost-effective and eco-friendly, eco-conscious infrastructure with minimum risk. Now, today we are talking about building big. Smart cities are what is the future, and tall buildings, heavy industry, infrastructure like industrial plants, power plants, refineries. In the transportation sector, we have railways, metros, roads and bridges, high-rise buildings, commercial as well as residential, culture, art and architecture. Now, the artificial intelligence, as you know, is a game changer, and things have changed a lot with the introduction of artificial intelligence. But for the geotechnical engineer, the future is without limit because geotechnical engineering services are required for all activities. Let's look at the challenges. Tall buildings, we are talking about the 30, 40 story to 100-story buildings, multiple basements, 3, 4 basements also are coming up now, thermal and solar power plants, heavily loaded industrial buildings, bridges and embankments for highways and railways. Now, when there is a lot of variation in the ground profile along alignment of metro tunnels, highways and railways, expansive soils is another challenging problem which has to be resolved, particularly in the Deccan area. Construction in weak and poor ground, liquefiable soils. So earthquake is very critical issue. Fractured rock, hill area development, landslides, dams, embankments. All these things now the geotechnical engineer has to take care of. And now the projects are all fast track projects. So the demands of fast track projects are that you have to have safer, sustainable, and smarter solutions. You have to come up with solutions for complex problem in minimum time. Respond quickly to keep up with the pace of demands of these projects. So design parameters have to be more realistic. Conventional approaches may just not be enough. You can't talk about a very high factor of safety. You have to squeeze the factor of safety, but you have to make sure that innovation, safety, and economy, these go hand in hand. So the geotechnical engineer plays a key role in evaluating the subsurface conditions for safe and stable foundations, designing solutions for challenging terrains, delivering cost-effective and eco-conscious solutions. So this shall empower the geotechnical engineer to create safe and sustainable future-ready infrastructure, bridging technology with environmental responsibility. Let's try to understand risk. Every project has a risk. And so risk is there everywhere when you start geotechnical civil engineering projects. But inadequate geotechnical assessment can lead to incorrect decisions. The famous Leaning Tower of Pisa, inaccurate assessment of the soil condition stability contributed to the tilt. Extensive stabilization efforts have been done over the past 2 decades to prevent the collapse of this tower. Wrong estimate of excavation quantities. The Sydney Opera House, it resulted in cost and time overruns and resulted in significant construction delays for this iconic building. Improper assessment of depth of liquefaction during earthquakes. This can be disastrous, can lead to liabilities and casualties. This is the Shanghai building collapse, which happened in 2009, probably due to liquefaction of the sands below the water table. Very recently here in Kerala, there was a highway collapse. You can see the consequence of this collapse. So catastrophic failures like the bridge in Bihar, this excavation in Bombay. Here, this is the TBM collapse in Kolkata. Now, you have to be aware that whether or not you do the site investigation, you end up paying for it. So that's what has to be, you have to be aware of it. So geotechnical engineering is always the hidden bedrock of any project. You can see that in 2010 to 2021, cost overrun on infrastructure projects has been nearly 18 to 20%. And primarily, most of this is due to the foundation issues. So let's start exploring the earth. This gentleman here peeping down, trying to figure out what the soil is. This is not something which can easily be done. So we have to look at the other alternatives. So let's look at the various levels of geotechnical input. This is called the geotechnical input pyramid. So this pyramid goes from bottom, bronze, silver, gold, and platinum. So this explains the quality of data generated by the geotechnical investigation. So bronze level investigation is sketchy and foundation design based on limited data. Usually the designer tends to be conservative, but whether there is a risk or not, he doesn't know. And where ground conditions are weak or unusual, vital information may be missed out and may result in unsafe design. So the quality of data has improves as you move up along this pyramid. So a gold and platinum level, the ones which have very low risk, you are very much clear. But of course, the cost of the gold and platinum level may be much more than bronze or silver level investigation. But you have to realize that what you spend additional in the geotechnical investigation, you would recover multiple times in the foundation cost itself. So don't save on the geotechnical investigation scope. It could result in unreliable foundation design and high foundation cost. Go for a platinum or gold level investigation, irrespective of the project size. It can lead to generation of good quality data, greater reliability in the foundation design, a higher factor of reliability rather than a higher factor of safety. So savings in foundation cost and time of construction, that is really what you're looking for. Geotechnical investigation practices have undergone revolutionary changes in the past 2 decades. Conventional boreholes with SPT, sample collection, and laboratory testing are now being supplemented with several in situ tests to model soil behavior. These include SPT energy measurement, electric cone penetration test with pore water pressure measurement, pressure meter tests, geophysical tests, and various other tests. The electric cone penetration test, also called the CPTU, is gaining popularity in the Indian construction industry over the past few years. Very effective for site characterization and to identify the subsurface conditions. So these tests should be included in the scope of the investigation. So I'm now going to present to you 3 case studies illustrating the application of geotechnical engineering concepts for foundation design, various challenging situations. The first one is a 42-storied residential commercial tall building, a tower in Gurgaon here in Haryana, grain silos in rural Kanpur in UP, and wind turbines in liquefiable silts in Kutch, Gujarat. The first case study which I'll be talking about is a 42-storied residential commercial building, a tall building in Gurgaon. So the site covers an area of about 11.4 acres, a high-rise housing complex consisting of 11 42-storied towers with 2 basements. Other facilities planned include a clubhouse, tennis and volleyball court, swimming pool, etc. The project is planned in 4 phases, 3 towers, clubhouse and swimming pool in the first phase, 3 towers in the second phase, and 2 towers in the third phase, 3 more towers in the fourth phase. So the tower building is a framed structure with a podium. 3 towers shall be constructed on a common raft bearing at 11-meter depth. The net bearing pressure coming on the raft exceeds 1300 kPa. So a hybrid pile raft system was used to support the structural loads. So this is the architect's visualization of the 3 towers on a common raft. And you can see here these 11 towers. So these 3 towers here, 3 towers here, 2 here, and 3 again. So these are the conceptual layout plan here. So the investigation scope, it covered 22 boreholes to 60-meter depth and 5 to 30-meter depth. Then SPT energy transfer ratio was measured for the rigs used. So in this, what you do is you standardize the SPT value corresponding to 60% energy transfer. 43 electric cone penetration tests were also done, and pressure meter tests were done in 4 boreholes. 3 crosshole seismic tests were done to 60-meter depth. 5 electrical resistivity tests. So advanced geotechnical investigation methods like CPTU, pressure meter, are now being routinely used on these important projects. The advantage is the quality of data is reliable, and you can justify higher bearing capacities in most cases, higher pile capacities from in compared to that you can get from conventional analysis. So let's look at the geotechnical investigation being done here. I'm going to present towers T1 to T3. So here I had 6 boreholes, 7 cone penetration tests, and pressure meter test in 1 borehole and crosshole seismic test in 1 borehole. So you can see the investigation drilling borehole in progress and the CPTU in progress here. So also the crosshole seismic test and pressure meter tests. So this is the layout plan for these 3 towers. You can see the location of the various boreholes and CPTs, pressure meter, crosshole seismic test, So this is the profile of the boreholes. So what we are getting here is all alluvial silt with some sand layers in between. Mm. So primarily this is silt, and below some depth here, SPT values are very high, and the N values are exceeding 100 below this depth here. This is the strata which we interpreted from the CPTU. Some locations there were a little bit more sand layers, but most of these tests met refusal at around 30 meters. SPT energy measurement was done. So here you have a instrumented drill rod, which has 2 accelerometers and 2 strain gauges. And the data acquisition was done using the SPT analyzer. So what we found is that the average energy transfer was about 75.1% in this particular case. Now the pressure meter tests. Here you have a pressure meter probe which is expanded in the borehole at different depths. You get a pressure versus volume curve, and what you determine is the limit pressure, the deformation modulus, and the horizontal stress versus depth at different depths the test was done. And you can see the profile of these various parameters with depth. The cross-hole seismic test. Here you have 3 boreholes adjacent to each other, and one borehole energy is generated, and there are receiver geophones in the other 2 boreholes, and they receive the energy. So from that you can determine the shear wave velocity and the compression wave velocity, and from that you can calculate your dynamic Young's modulus and dynamic shear modulus. This is the CPT data, the average profile from the various CPT done at the 3 tower locations. This is the average cone resistance here, and of course the sleeve friction ratio, pore water pressure measurement. You can see the soil strata interpreted from the, I think, primarily cohesive soils with some sand layers in between. So now with the using the CPT data, what we did was we tried to interpret what the how it correlates with the various geotechnical parameters like SPT. So you can see here the average CPT interpreted SPT N60, that is the 60% energy transfer, compared with the actual borehole data. This is the bulk density of from the undisturbed samples compared with the borehole data. The undrained shear strength of the cohesive soil, again compared with the interpreted from CPT. Then you have the constraint modulus, the shear modulus, shear wave velocity computed from the cross-hole seismic test has been superimposed on this. You can see there is a very good match here. So looking at all this data, this is the design profile that was developed. And so we had primarily sandy silt nearly to about 23 meters. And then there is a silty sand layer between 23 and 30 and below 48-meter depth. So we did the bearing capacity analysis. As you know, bearing capacity analysis and settlement analysis is done for foundations. And what you would like to do is you would select the lower of the 2 values from the bearing capacity analysis and the settlement analysis. So the bearing capacity analysis was done for the isolated foundations and raft foundations. Conventional analysis using the C5 values as per IS 6403. Then, of course, the CPT profile using the correlations given by Robertson, and also pressure meter test. So you can see for we calculated for a 3 meter by 3 meter size foundation at 9 and 11 meter depth. Well, the conventional analysis gives you a value much lower than what you would interpret from the CPT or the pressure meter. So looking at these numbers, a somewhat middle value was selected for foundation analysis. So we picked 550 kPa at 9 meter and 650 kPa at 11 meters. And for a 10 by 10 meter size raft, the analysis was indicated again the similar kind of trends, and 600 and 665 was selected at 9 and 11 meter depth. So this was the upper limit. So we would have to now check with the settlement analysis to decide what would be the allowable bearing pressure. So this is the bearing capacity plots at 9 and 11 meters for a 3 meter by 3 meter and a 10 meter by 10 meter size foundation. Now the settlement analysis, again using the three methods, we were able to assess the settlement. For isolated foundations, a permissible settlement of 50 mm was considered, and for raft foundations, permissible settlement was taken as 75 mm. So using this, the selected values, now when you are having the pre-analysis, you have to restrict it from shear, whatever you got in shear. So these are the numbers which were selected for the foundation design. So again, this is the settlement analysis for a 3 meter by 3 meter and a 10 meter by 10 meter size raft. So the lower of the two values were selected. So isolated foundations, 550 kPa at 9 meter depth and 650 at 11. Raft foundation, 580 at 9 and 650 at 11. Now you can see if you had done by the conventional analysis, you would have been in the range of 400 to 450, which has been increased substantially to up to 650 for the raft. So you have got about 21% higher for isolated foundations and 19% higher for the raft foundations. So this is a huge saving in the foundation cost. But what was done actually was a hybrid pile raft foundation was used, and the piles were used as a settlement reducer because the applied bearing pressure was coming around 1300 kPa. So 1000 mm diameter, 30 meter and 35 meter long pile were analyzed with cutoff level at 11 meters. So again, the three different analyses were done using the conventional approach, the CPTU and the pressure meter. So for 30 meter long pile, you can see the CPT was giving the maximum higher capacity, but the conventional was the lowest in all cases. Reviewing all this, what was done is that we selected a value of 3900 kilonewton for a 30 meter long pile and 4400 kilonewton for a 35 meter long pile, corresponding ultimate capacities. You can see 11,700 and 13,200 kilonewtons. So this obviously represents a 20 to 23% increase in the safe pile capacity compared to the conventional approach. So the soil structure interaction was then done using Plaxis 3D software for the design of the pile raft foundations. The soil layers were modeled as linearly elastic, perfectly plastic materials following the Moore-Coulomb yield criteria. Raft and piles were modeled as linearly elastic materials. The purpose of the soil structure interaction is to assess the load sharing between the raft and the piles. This will help economize the design and reduce the number of piles. Since the piles are being used as a settlement reducer, the piles can be loaded substantially beyond the computed safe capacity as long as the total and differential settlement of the raft is within the permissible limits. Thus, you can achieve substantial economy. So these are the input parameters, the 2-meter thick raft, a concrete grade M50. So you can see the E values, unit weight, Poisson's ratio for the concrete raft foundation, obviously at 11-meter depth. We had 35-meter long piles from the cutoff level of 11 meters. So this is the foundation layout, the 3 towers. The first cut analysis was done using raft without piles. As per the analysis, the computed settlement of the raft was 272 mm. Obviously not settlement tolerable for the structure because the IS 1904 permits a maximum of 125 mm. So we had to go for piles. So this is the hybrid pile raft foundation model. Both cast in situ piles, 1000 mm dia, 35 meter below the cutoff level. So piles are being reduced as a settlement reducer. So we loaded the piles much beyond the safe load. A center to center pile spacing of 3.4 meter in triangular grid pattern was used to meet the permissible settlement criteria. So this is the pressure contours below the base of the raft. And this is the settlement contours at the base of the raft. The maximum settlement of the raft was 39 mm. And angular distortion was 1 in 515. What the permissible value is 1 in 500. So this is safe. So most of the piles was applied. The load was around 7,000 to 8,000 kilonewtons. This is 53 to 61% of the ultimate pile capacity. Only one pile was loaded to about 76% of the ultimate pile capacity. So based on these displacements and the load transfer, the zoned spring constants were determined. The zones were all identified here. And this is the pile layout. A total of 312 piles were used. And over the piles, you had a 2-meter thick raft. With this, I move on to the second case study, grain silos in rural area of Kanpur for storing grains. So this is the layout plan. Here, 2 boreholes to 30-meter depth and conducting SPT at every 1.5 meter intervals was done. SPT energy transfer was measured, and 4 cone penetration tests were also done. So this is the photograph showing the investigation in progress, the CPTU and the data acquisition. The boreholes and stratigraphy interpreted from the CPT, you can see below around 10-11 meter depth, sand is encountered. The upper layer is silt. Water table is met around 4 meter depth. So this is the stratigraphy here. Again, SPT energy measurement showed me an average energy transfer of around 71.4%. So this is what was used here. So you can see N60 versus depth. The actual field N value is shown in this dotted red, and after correction, you get this corrected SPT values. Similarly, typical plot of CPT here, cone resistance, slip friction, friction ratio, pore water pressure, and soil behavior type. We compared it with the borehole data. You can see here again whether it is SPT, undrained shear strength, friction angle. Of course, friction angle was somewhat lower compared to what you get from the direct shear test in the lab. Otherwise, all the parameters are showing good match. Similarly, constraint modulus, Young's modulus, and overconsolidation ratio have also been interpreted from the CPT data. The geotechnical design profile based on CPTU, you can see the top, you have the cohesive soils, and then you have the sand, and then below 24 meters, again, there is a clay layer. So E-values were interpreted from various correlations. So you can see here due to CPT, the E-value increase was substantial, between 42 and even 57%. So bearing capacity analysis, again, we did it for 3 meter by 3 meter size foundation and a 6 meter by 6 meter foundation at 2 meter depth. And you can see from the IS code approach and CPT Robertson approach for a permissible settlement of 50 mm, there is a increase of 74%. Similarly, for a 6 meter by 6 meter size foundation at 2 and 4 meter depth, you get about a 48% increase. Also, the silo was a 32 meter diameter circular raft. Here we got an 100% increase in SBC value. So obviously, this is the impact here. We were able to interpret much higher values. This is the 3 meter size foundation, and then the 6 meter size foundation, and then this is the 32 meter diameter raft. So obviously, since the bearing capacity increased substantially, so ground improvement was not required for the 32 meter raft. So conventional analysis had suggested only 110 kPa, but because the loading was much higher, the decision at earlier was that we should go for stone columns to increase the bearing capacity, but we could prove from the CPT that it is not required. So huge saving, extra large financial cost, as well as 2-3 months to install the stone columns. So the CPT proved that the natural soils will be able to support the silo foundation. The saving here was very substantial, on the order of about 3.5 lakhs per silo, 3.5 crores per silo, about 7 crores for 2 silos, whereas the cost of additional testing was only 5 lakhs. So that's around 14,000% of the return on investment by just using the CPT. I now move on to the third case study, wind turbines in liquefiable silt. We have to realize that even silts can liquefy under certain conditions. Renewable energy and wind turbines, these are something which are now the talk of the country. India's renewable energy goals and global transition to cleaner energy has spurred installation of these wind turbines to harness wind energy to boost energy generation. Now, 50% of the power is targeted to be generated from renewable energy, renewable sources over the next few years. So about 4 gigawatts of wind energy-based power will be generated from the Kutch region. The Kutch region, western Gujarat, witnesses high solar radiation making it ideal for solar energy generation. It is also blessed with one of the best resources, wind resources availability in India, with speeds of up to 8 meters per second. So this says that we can generate power from solar energy as well as wind energy. So to boost the wind energy capacity, India's largest onshore wind turbine farm is coming up in Kutch. Each turbine is capable of generating about 5.2 megawatts of electricity. Now, hundreds of these turbines are being installed in that area. The turbine shall have a rotor diameter of 160 meters, and the tip height is 200 meters. So here I will be presenting one typical wind turbine in the soft non-plastic silts. It explains the characterization of these soils and the implication for design. So at each turbine location, we did one borehole 25-meter depth, one crosshole seismic test, and one electric pole penetration test, also one electrical resistivity test. So you can see the borehole in progress here and the CPT being done. The geology in this area is that this area came under marine transgression during the Jurassic period. The soils in the area are coastal alluvial sediments, and they are characterized by high salinity and shallow water table. So this is the CPT results. You can see what it is, a firm to very stiff non-plastic sandy silt. SPT values 4 to 8 to 11 meter depth, 10 to 15 to 20 meter depth, and 16 to 20 to 25 meter depth. Groundwater at 6 meter depth. Worst condition because it's very close to the sea. It wasn't considered to rise to ground level. So the results of the crosshole seismic test, you can see the wave velocities, shear wave velocity, and the shear wave velocity and the primary wave velocity. From this, we interpreted the dynamic modulus and shear modulus. The CPT, you can see the very good match with the SPT borehole data. Similarly, the density also shows a good match. Shear undrained shear strength also very good match. Constraint modulus and shear wave velocities from the crosshole seismic test. So a constraint modulus, of course, is 1 by MV. So you can use this for the consolidation characteristics. Now look at the soil gradation. So you can see here that the sand content is 25 to 35%. The silt content is 67 to 78%, with clay content of less than 3%, and less than, that is 0.002 mm. 0.005 is 9 to 12%. This is the moisture content and liquid limit profile. Low liquid limits, significantly less than 25. The moisture content is close to the liquid limit. So as far as the plastic limit is concerned, we couldn't determine. It is non-plastic. It cannot be rolled into a 3 mm diameter thread. So this is a non-plastic silt with moisture content very close to the liquid limit. Now, liquefaction analysis was done. This area is in zone 5, earthquake zone 5, design magnitude of 7.5, peak ground acceleration of 0.36 G. SPT automatic hammer was used, and the design groundwater table depth was at ground level. So now the analysis method, SPT values and gradation characteristics as per the IS 1893/2016. So, and also the NCEER summary report given by Youd and Idris based on the CPT resistance as well as the shear wave velocities and SPT. So the NCER approach suggests that cohesive soils, which contain more than 50% silt below silts and clays below the water table with low N values will be prone to liquefaction if the percentage of particles less than 5 microns does not exceed 15% and the liquid limit is less than 35%, and if the moisture content is more than 90% of the liquid limit. So this is the result because this it was meeting these criteria. So the analysis showed me that based on SPT values, the liquefaction depth was 20.5, and based on CPT, it is 19.5. And from shear wave velocity, it is around 24 meter. So these are the CSR, CRR factor of safety plots, which is showing me that factor of safety less than 1 to substantial depth. Similarly, from the CPTU, there is it is showing substantial liquefiable results, and also from the shear wave velocity. So this is just plotted here for your convenience. So with this, I conclude that geotechnical engineering is in the field requires a clear understanding of soil behavior. Selection of foundation type should be done on the basis of a well-planned and detailed geotechnical investigation. Assessment of the technical requirements and also assess the risks properly so as to tailor the scope of investigation to determine the critical parameters that influence the safety of the structure. A judicious inclusion of advanced in situ tests like CPTU, pressure meter, geophysical test is required for a better assessment of safe bearing capacity. Now, CPTU and pressure meter profiles give a much more realistic and reliable evaluation of the foundation behavior. The good quality data can be correlated very well with the various engineering parameters. In comparison to conventional analysis using borehole data only, these tests can, in situ tests can justify safe higher bearing pressures, thus eliminating the need for ground improvement or piles. With better understanding of technology, geotechnical engineers can ensure reliable and economical foundation designs. The cost benefits that can be reaped by performing advanced tests such as CPTU, pressure meter, SPT energy measurement, geophysical tests, this can be enormous. But to be able to do this successfully, you have to live with the soil, breathe into its soul, and be a part of it, understand how it behaves, and contribute to understand the soil behavior and be able to assess what is required. Thank you very much. I'll be very happy to take questions. I'd like to end by saying that geotechnical engineering is a science, but its practice is an art. Thank you.
I have one question, sir, regarding this high-rise building in Noida. So,
yes, sir.
Yes, sir. So the soil is almost silty and up to a depth of 60 meters. So you have adopted the piled raft foundation. Whether any liquefaction analysis has been done, sir? Since,
yes, liquefaction analysis was done. I didn't include it here. Here the soils were non-liquefiable. So let me go to the strata here. If you can see, the soils are mostly silts, very small thin sand layers. So therefore these were not prone to liquefaction.
So on behalf of School of Civil Engineering, we thank you very much, sir, for sparing your valuable time and sharing your knowledge to our civil engineering students. Thank you very much, sir.
Thank you very much. I hope that the students were able to get some benefit out of this, or it went a little above their head. I don't know. If there is something which you people would like to reach out to me, I'll be very happy.
Once again, thank you very much, sir, for
thank you.
sharing valuable time.
My pleasure connecting to you.